To look at the relationship between K subscript A for acid and K subscript B for bases, I'm going to look at two examples. The first examples, I will look at a salt such as ammonium chloride. Now salts dissociate 100% when they are in liquid water, if they are soluble. In this case it is very soluble, so it will give you 100% ammonium and 100% chloride. Now chloride then again is spectator, but ammonium is going to make some sort of reaction with water. Let's just see what it does and if we can bring that relationship of Ka and Kb to life. Ammonium is going to react with water in the fashion as a species that is going to donate a proton, therefore it's a Bronsted acid. Water is going to accept it from it, and it's going to establish an equilibrium to give you ammonia plus H3O plus. Now ammonia is your conjugate base and hydronium is your conjugate acid. Since this is how I wrote it, ammonium is your acid, and I can write dissociation constant for it, or equilibrium constant, subscript A, which is my product, ammonia times hydronium divided by ammonium only. Do not include water because it's pure liquid. So liquid, the rest of species are aqueous. Okay, let's hold on to this. So this is dissociation constant of the acid ammonium. Now let's just look at the reverse. It's equilibrium. Let's see what happens to ammonia when it reacts with a water molecule. In this case, it behaves as a Bronsted-Lowry base. It's going to accept a hydrogen from water. So ammonia is a base, a weak base, and this is your acid, Bronsted acid. Double arrow for equilibrium gives you ammonium, a conjugate acid, and from H2O you have hydroxide left over, a conjugate base. Now since in this direction ammonia is a base, I can write K subscript B for a base, which is products ammonium times hydroxide divided by ammonia only. Then again we exclude H2O because it's pure liquid. Now what happens if I take this Ka and this Kb here and multiply them by each other? Let's see what happens when I do Ka multiplied by Kb. What I have is this ratio multiplied by this ratio. Let's just bring it down. So this is my Ka, which is ammonia times hydronium over ammonium multiplied by Kb, which is this ratio of ammonium multiplied by hydroxide divided by ammonia. Now a few terms we can cancel. Let's do that. Ammonia and ammonia, they cancel each other out. Ammonium and ammonium go away. The leftover is hydronium times hydroxide. So what we can conclude is Ka multiplied by Kb is hydronium or hydrogen ion times hydroxide, which is nothing but Kw. Therefore, Ka multiplied by Kb is Kw, and it's equal to that number at 25 degrees Celsius. So this is what we should remember if we are missing a Ka or Kb. I'm going to do the same treatment for now another salt. Let's say we have sodium ethanoate. So NaCH3COO. Sometimes we put the plus and minus 2. Now then again, is a salt is going to dissociate 100% in water. It will give you sodium ion spectator ion, and it will give you acetate or ethanoate, which is going to react with water. Let's look at that reaction. So ethanoate plus H2O. In this case, H2O is behaving like an acid, a Bronsted acid, and CH3COO minus will be a Bronsted base. Base, acid, double arrow for equilibrium. CH3COOH, a base accepts a proton from an acid, so this is ethanoic acid, this is your conjugate acid. Leftover of H2O is OH minus, which is a conjugate base. Since this is direction of a base ethanoate, I can write Kb, which is my product, CH3COOH multiplied by hydroxide divided by CH3COO excluding H2O. Now let's look at the reverse. What happens when ethanoic acid or acetic acid reacts with water? Ethanoic acid is an acid, behaves like one, donates the last hydrogen, which is loosely held, to your base water in this reaction. The leftover is CH3COO minus, which will be your conjugate base. These two are related by a swap of proton, and hydronium ion, which is always a conjugate acid. Now if I write Ka, because this is the acidic direction, equilibrium constant for that, product CH3COO minus times hydronium divided by ethanoic acid CH3COOH, we can prove the same point, that if you take Ka and you multiply it by Kb, you will get Kw. Let's see if this is true. So I'm going to take this, multiply it by this. So down here, CH3COOH multiplied by hydroxide divided by ethanoate, CH3COO, times your Kb, CH3COO, times hydronium divided by CH3COOH. Like terms cancel each other out. The leftover is our proof that Ka times Kb is nothing but hydroxide times hydronium. Therefore, the same conclusion as before, except not if we went after ethanoic or a salt of ethanoate, times Kb is equal to Kw. So let's remember this relationship. If you are missing a variable Ka and you have Kb, by knowing Kw, which you already have memorized, you should bring the other one to life.